Welcome! In this session, we will be exploring an interesting problem titled Remove 9, where we'll dive into how to generate a sequence of integers while skipping numbers containing the digit 9. Stay tuned as we walk through the problem, its challenges, and efficient solutions. The problem is to determine the nth number in a sequence where all integers containing the digit 9 are excluded. For instance, in this sequence, numbers like 9, 19, and 29 are skipped entirely. The input to the problem is a single integer, n, which represents the position in this altered sequence. The output is the integer at that specific position. The task requires us to carefully construct this sequence while ensuring that any number containing the digit 9 is omitted. For example, if the input is n equals 9, the output is 10. Here's why. The sequence begins as 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, where numbers like 9 are skipped because they include the digit 9. The ninth number in this sequence is therefore 10. Similarly, when n equals 19, the output is 21. If we extend the sequence further, we see it becomes 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13, 14, 15, 16, 17, 18, 20, 21. The 19th number in this sequence, after excluding all numbers containing the digit 9, is 21. Now, consider a larger example. If the input is n equals 50, the output is 63. In this case, the sequence continues as 1, 2, 3, 62, 63, 64, where all numbers with the digit 9 are skipped. The 50th number in this sequence turns out to be 63. The problem also specifies important constraints. For example, n can range from 1 to 10⁻8, meaning the solution must handle cases where n is an extremely large number. Additionally, for smaller inputs like n equals 1, the output is simply 1, as this is the first valid number in the sequence. To summarize, any number containing the digit 9 is excluded from the sequence. This means numbers like 9, 19, 29, and so on do not appear at all. For larger values of n, such as 10⁻8, it is critical to efficiently calculate the result without explicitly generating the entire sequence up to the nth number. Instead, we need an optimized approach that directly finds the nth valid number without including invalid numbers containing the digit 9. When approaching this problem, the brute force method seems like an intuitive starting point. The idea is simple: we generate the sequence of integers one by one, skipping any number that contains the digit 9. To determine whether a number should be skipped, we can convert it to a string and check if it contains the character 9. While this method works, it's important to note a few observations. First, the sequence grows more slowly than the natural numbers because we are omitting all numbers with the digit 9. Second, while checking for the digit 9 in each number is straightforward, the brute force approach becomes increasingly inefficient as n grows larger. This is because we end up iterating through a lot of numbers, including those that will ultimately be skipped. The time complexity for this approach is O(k), where k represents the total count of numbers, including the skipped ones, needed to locate the nth valid number. For large values of n, this inefficiency becomes a significant drawback, making the brute force approach impractical for most cases. To address the inefficiency of the brute force approach, we can turn to an optimized solution that leverages the concept of base 9 number systems. In a base 9 system, numbers are represented using only the digits 0 through 8, which means the digit 9 is naturally excluded. For example, in base 9, the number 1 in base 10 remains 1, 2 in base 10 remains 2, and so on up to 8. However, the number 9 in base 10 is skipped entirely, and the next number, 10 in base 10, becomes 11 in base 9. This direct mapping allows us to bypass the need to check and skip individual numbers containing the digit 9. To find the nth number in the sequence, we can simply convert n into its base 9 representation and then interpret the result as a base 10 number. This approach is efficient because the base 9 representation guarantees that no invalid numbers are included. The key insight here is that by working within a base 9 system, we eliminate the need for unnecessary computations entirely and directly obtain the desired result. Let's break down the steps involved in the optimized approach. First, we convert the given n into its base 9 representation. This can be achieved using repeated division and modulo operations, where we repeatedly divide n by 9 and track the remainders to construct the base 9 number. Once we have the base 9 representation, we interpret it as a base 10 number to produce the result. This direct mapping allows us to efficiently determine the nth number in the sequence without generating or checking intermediate values. Because the conversion process involves repeatedly dividing n by 9, the time complexity of this approach is O log n, which is significantly faster than the brute force method, especially for large values of n. The optimized approach using base 9 conversion emerges as the clear choice for solving this problem due to its efficiency and elegance. While the brute force approach is conceptually simple, it becomes increasingly impractical for large inputs since it involves iterating through and filtering out many invalid numbers. On the other hand, the base 9 strategy transforms the problem into a mathematical one, enabling us to directly compute the result without any unnecessary overhead. The trade-off here is that the base 9 method requires a slightly more complex implementation, but this is outweighed by its dramatic improvement in performance. The aha moment lies in recognizing that skipping the digit 9 is equivalent to working within a base 9 number system. This insight allows us to bypass the need for manual filtering entirely, making the base 9 approach not just optimal but also elegant in its simplicity. For these reasons, the base 9 conversion method is our chosen strategy. In this problem, we are tasked with finding the nth number in a sequence where all integers containing the digit 9 are excluded. For example, the sequence begins as 1, 2, 3, up to 8, then skips 9 and continues with 10, 11, 12, and so on. The challenge is to determine the nth valid number as efficiently as possible. To achieve this, we start by initializing two variables. Count is set to 0 to track how many valid numbers have been found, and current is initialized to 1, representing the number currently being checked. Then, we use a while loop to iterate through integers in sequence, stopping only when we identify the nth valid number. During each iteration, the algorithm converts the current number to a string and checks whether it contains the digit 9. If 9 is present, the number is skipped, as it is invalid in our sequence. If a number does not contain the digit 9, it is considered valid, and we increment the count variable by 1. Once count equals n, the algorithm terminates, and the current number is returned as the result. Regardless of whether the number is valid or not, we always increment current at the end of each iteration to proceed to the next integer. This ensures that every number is checked systematically. By filtering out numbers with 9, the algorithm efficiently avoids unnecessary increments to the count variable, focusing only on the valid numbers. Additionally, the loop stops as soon as the nth valid number is found, ensuring the process does not run longer than necessary. This approach leverages simple string operations to identify invalid numbers while keeping the implementation straightforward and efficient. The algorithm relies on simple data structures to achieve its goal. The variable count is used to track how many valid numbers have been found so far, while current keeps track of the number being examined at any given moment. A key operation in this solution is converting integers to strings, which allows us to easily check if the digit 9 is present using a substring check. This avoids the need for additional digit manipulation, simplifying the implementation. The substring check itself is efficient, with a time complexity of O, d, where d is the number of digits in the current number. By incrementing current after each check and looping until we reach the nth valid number, the algorithm ensures that all numbers are examined in sequence, skipping those that contain 9 as needed. Analyzing the complexity of the algorithm, the time complexity primarily depends on the number of integers checked until the nth valid number is found. Since approximately 10% of integers contain the digit 9, the algorithm checks about 1.1 times n numbers in total. For each number, the substring operation to check for 9 takes O, d, time, where d is the number of digits in the number. Therefore, the overall time complexity is approximately O, n asterisk d. On the space side, the algorithm is highly efficient, using only O1 extra space. This is because it relies on a small number of variables, such as count and current, without requiring additional data structures. Edge cases to consider include handling n equals 1, where the first valid number is simply 1, skipping numbers like 9 and 19 correctly, and ensuring the algorithm performs efficiently even for large values of n. To clarify the algorithm, let's walk through an example with n equals 15. We begin with current equals 1 and count equals 0. The algorithm checks current equals 1, which does not contain 9, so count as increment to 1. Next, current equals 2 is checked, and since it is valid, count becomes 2. This process continues, incrementing count for each valid number while skipping numbers like current equals 9 that contain the digit 9. By the time count reaches 8, the algorithm will have skipped 9 and proceeded to valid numbers such as 10, 11, and so on. Eventually, when count reaches 15, the algorithm identifies the 15th valid number as 17. This demonstrates how the algorithm systematically skips invalid numbers while efficiently finding the desired nth valid number. This solution solves LeetCode problem remove 9 by leveraging a mathematical property of numbers in base 9 to efficiently skip integers containing the digit 9. Explanation. The sequence described in the problem is equivalent to representing numbers as if they were in base 9, where digits range from 0 to 8 instead of 0 to 9. By treating the sequence as base 9, we can directly map the input n to the corresponding number in the sequence without checking each number individually. Step-by-step breakdown asterisk. 1. Start with result equals 0, which will store the number corresponding to the given n in the sequence. 2. Use a variable base initialized to 1. This represents the place value in the base 9 system, e.g., ones, tens, hundreds. 3. While n is greater than 0. Extract the last digit of n in base 9 by computing n%9. Multiply this value by the current base and add it to result. Update n by performing integer division with 9, n // equals 9, effectively moving to the next digit in base 9. Multiply base by 10 to shift to the next place value in the decimal system. 4. When the loop finishes, result contains the number corresponding to the nth position in the sequence. Why this works asterisk. Numbers in base 9 naturally exclude the digit 9. By treating the sequence as a conversion to base 9, we can directly compute the result without iterating through all integers and manually skipping those that contain 9. This makes the solution highly efficient. Complexity analysis asterisk. Time complexity asterisk O log n, as the loop runs once for each digit in the base 9 representation of n. Space complexity asterisk O 1, as no additional space is used beyond a few variables. This approach ensures optimal performance and avoids unnecessary computation, making it well-suited for large inputs. This is the Java implementation of LeetCode problem number 660, remove 9. The solution leverages base 9 conversion to skip numbers containing the digit 9. The key difference from Python is the explicit type declarations and use of Java's class structure. The logic mirrors the Python implementation, ensuring the same functionality in Java. To solve LeetCode problem number 660, our objective is to determine the nth number in a sequence where all numbers containing the digit 9 are removed. This modified sequence begins as 1, 2, 3, 8, 10, 11, skipping over any number with a 9. Instead of iterating through all numbers and manually checking for 9, we can solve this problem efficiently using base 9 representation. Let's explore the example where n equals 8. Initially, we start with result equals 0 and base equals 1. In the first iteration, we compute n%9, which equals 8. This means the last digit in the base 9 representation is 8. We add 8 asterisk base to result, updating result to 8. Then, we update n by performing integer division by 9, which sets n to 0. Finally, we multiply base by 10, setting it to 10. At this point, since n is now 0, the loop terminates, and we have our answer. The final state of the first example confirms that result equals 8. This makes sense because the 8th number in the sequence is simply 8, as there are no skipped 9s before it. Now, let's consider another example where n equals 9. We initialize our variables with result equals 0 and base equals 1. In the first iteration, we calculate n%9, which equals 0. This tells us the last digit in the base 9 representation is 0. We add 0 asterisk base to result, leaving result unchanged at 0. Then, we update n by performing integer division by 9, which sets n to 1. Finally, we multiply base by 10, updating it to 10. At this point, we need to continue to the next iteration since n is not yet 0. In the second iteration for n equals 9, we calculate n%9 again, which now equals 1. This tells us the next digit in the base 9 representation is 1. We add 1 asterisk base to result, updating result to 10. Next, we update n by performing integer division by 9, which sets n to 0. We also multiply base by 10, updating it to 100. Since n is now 0, the loop ends. The final state shows that result equals 10. This means the ninth number in the sequence is 10. Why? Because all numbers containing the digit 9, like 9 itself, are skipped, and the sequence instead directly jumps from 8 to 10. Let's examine a third example with n equals 20. We begin with result equals 0 and base equals 1. In the first iteration, we calculate n%9, which equals 2. This indicates that the last digit in the base 9 representation is 2. We add 2 asterisk base to result, updating result to 2. Then, we update n by performing integer division by 9, which sets n to 2. We multiply base by 10, updating it to 10. Now, since n is still not 0, we proceed to the second iteration. In the second iteration for n equals 20, we compute n%9 again, which equals 2. This tells us the next digit in the base 9 representation is also 2. We add 2 asterisk base to result, updating result to 22. Then, we update n by performing integer division by 9, which sets n to 0. We also multiply base by 10, updating it to 100. Now that n is 0, the loop ends. The final state confirms that result equals 22. This means the 20th number in the sequence is 22. The reason this works is that base 9 inherently skips any number containing the digit 9. To summarize, the algorithm uses base 9 conversion to efficiently compute the result without explicitly iterating through and filtering numbers. This approach ensures correctness and runs in O, log, n time by avoiding unnecessary checks for invalid numbers. When analyzing the time complexity of this solution, the key operation to focus on is how we repeatedly divide the number n by 9 and perform a constant amount of work in each iteration. To understand this better, let's break it down. First, consider the number of iterations. In every loop, the value of n is reduced by a factor of 9, thanks to the operation n // equals 9. The loop continues until n becomes 0, which means the number of iterations is directly tied to how many times you can divide n by 9. This is essentially determined by the number of digits in n when represented in base 9. Mathematically, the number of digits in base 9 representation is approximately log_9, n, or equivalently, log_10, n, /log_10, 9. Next, during each iteration, we perform operations like modulus, division, multiplication, and addition. These are all constant time operations, meaning they each take O1 time. Combining these observations, the total runtime depends on the number of iterations, which is O log_9 n multiplied by the constant work per iteration. Since the base of a logarithm does not affect big O notation, this simplifies to O log n overall. Now turning to the space complexity, this solution is highly efficient in its memory usage. The algorithm only uses a few variables to compute the result to store the transformed number, base to track the current power of 10, and n for the input value being modified. All these variables are scalar values that do not depend on the size of the input, meaning their memory usage remains constant. Additionally, the solution avoids using any extra data structures such as arrays, lists, or recursion stacks. This ensures that the memory consumption does not grow with the size of the input n. Therefore, the overall space complexity is constant, or O1. To appreciate the efficiency of the current approach, let's compare it to a brute force solution. In a naive method, you would iterate through all integers from 1 to n and check each number to see if it contains the digit 9. For each number, this involves inspecting each digit, which takes O, d, time for a number with d digits. Since d is proportional to log n, the total time complexity for this method would be O, n asterisk log n. This is significantly worse than the optimized approach. By contrast, the current solution leverages base 9 conversion, which skips numbers containing the digit 9 entirely. Instead of iterating through all numbers, we directly calculate the base 9 equivalent, reducing the number of operations to a logarithmic scale. This makes the time complexity O log n and the space complexity O 1. In summary, this optimized approach is exponentially faster than the brute force method for large values of n. The base 9 conversion not only avoids redundant operations but also provides a mathematically elegant solution to the problem, making it the clear optimal choice. When working on this problem, there are a few common mistakes to be mindful of. The first is not recognizing the skipping pattern of numbers that include the digit 9. For example, after 8, the next valid number is 10 because 9 is skipped. Similarly, after 18, you jump directly to 20, skipping 19. If this irregular spacing isn't accounted for, it can lead to off-by-one errors when calculating the nth valid number. Another common issue is inefficiently checking for the digit 9 in numbers by repeatedly converting integers to strings. While this approach works, it can become very slow when performed in large loops. A better alternative is to use modular arithmetic to extract digits, which avoids the overhead of string conversions. Additionally, some developers misunderstand the problem scope, assuming the input n is small. This can result in solutions that fail to handle edge cases, like extremely large values of n. For example, when n is 10 to the power of 6, brute force methods become infeasible. To address this, always clarify the constraints and test edge cases thoroughly during implementation. Another mistake to watch out for is making incorrect optimization assumptions. For instance, some attempt to skip entire blocks of numbers, such as 90 through 99, without carefully verifying that no valid numbers are missed in the process. Any optimization like this must be rigorously tested to ensure correctness. Another pitfall is hard-coding specific ranges or digit limits, such as assuming n will always be less than 100. While this might work for small test cases, it fails for larger inputs and makes the solution inflexible. A robust solution should dynamically scale and adapt to the constraints provided. From an interview perspective, this problem is an excellent test of your ability to recognize patterns and solve sequence manipulation challenges efficiently. A brute force solution is often the starting point, but interviewers typically expect you to move beyond that by discussing optimizations. For instance, instead of iterating through all numbers, you could calculate the number of skipped values in a range directly. It's also important to demonstrate your awareness of edge cases, like handling n equals 1 or very large values, and ensure your solution works across all scenarios. Finally, be prepared to discuss trade-offs. For example, modular arithmetic offers greater efficiency, but some may find it less intuitive than string manipulation. Explaining these trade-offs shows a deeper understanding of the problem. This problem shares similarities with several other LeetCode challenges. For example, LeetCode 204, Count Primes, involves filtering numbers based on a condition, much like filtering out those containing the digit 9. LeetCode 728, Self-Dividing Numbers, requires checking properties of individual digits, which is conceptually similar. LeetCode 386, Lexicographical Numbers, focuses on generating numbers in a specific order, comparable to generating a sequence while skipping certain values. Finally, LeetCode 902, Numbers at Most N Given Digit Set, involves constraints on allowed digits, which aligns closely with the logic of skipping numbers based on digit restrictions. There are several approaches you can take to solve this problem, each with its own trade-offs. The brute force approach involves iterating through integers starting from 1 and skipping those containing the digit 9. While simple to implement, it's inefficient for large values of n due to its O, n*d, complexity, where d is the average number of digits. A more efficient method is counting valid numbers directly. This involves calculating how many valid numbers exist in specific ranges, such as 1 to 9 or 10 to 99, and using that information to determine the nth valid number. This approach has a complexity of O log n, but requires careful implementation. Another option is pre-computing the sequence of valid numbers up to a certain limit and storing them in an array. This enables O1 lookups but requires additional space and may not scale well for very large values of n. Each approach has its advantages, so choose based on the problem constraints and required efficiency. Great job! We've broken down the Remove 9 problem and explored the brute force approach. Remember the importance of balancing intuition with optimization while solving problems like this. Thanks for watching, and don't forget to subscribe for more engaging coding content. Until next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!